All right, so much for heat transfer and how the heat gets from the heating surfaces to the water through radiant, conductive, and convective forces. Now let's consider where this heat comes from and move into the subject of combustion. On the screen now you see various fuels, both gas and liquid, and the BTUs that are released by them per gallon or cubic foot of gas when they're combusted. The most prominent of the fuels burned today is natural gas, and that's why I have it listed first. And as you can see, it releases about 100,000 BTUs per therm, a therm being 100 cubic feet, and a cubic foot of gas being about 1,000 BTUs. So if we take this gas, or any carbon fuel for that matter, and volatilize it, a chemical reaction results with the hydrocarbons combining with the oxygen in the air to produce carbon dioxide and water. Now, the higher the CO2, the higher the combustion efficiency. And stated another way, the lower the excess air, the higher the efficiency. And we'll talk about that a little bit later. And then what you also see on the slide is that besides carbon dioxide and water being formed, we also produce heat. Now, for combustion to occur, we need time, temperature, and turbulence. Now, the burner obviously provides the temperature with the pilot flame initially, and the turbulence with its design features that we'll be looking at shortly. But what provides the time for combustion? What provides the time? Well, it's the furnace. It's the furnace and the boiler, which needs to be designed specifically for the burner, matching it to attain the time required for complete volatility and the highest combustion efficiency possible. Now, there's a whole lot of complicated engineering which goes into packaged and field-assembled boiler design, including combustion and heat transfer specialists, along with engineers specializing in structural design as they consider the metal's limitations when exposed to extreme heat and pressure. But okay, getting back to combustion, I'm sure many of you have heard the term stoichiometric combustion, or maybe you haven't. Well, if not, it means 100% complete combustion where there are no hydrocarbons or soot that remain, and there's zero excess air, and there's no CO or carbon monoxide. Well, everything has been volatilized cleanly. That's stoichiometric combustion. But you know, that's not the way we in the industry set burners up in the field to operate, as it leaves just no margin for error when conditions which are totally out of our control come into play. So we normally set burners to operate as close to 15% excess air. Now that's 15% over stoichiometric. And this we try to do as much as possible to maintain a safe and cost-efficient operation. Because, you know, things like ambient temperature in the boiler room, barometric pressure changes, relative humidity changes, all of these things are uncontrollable conditions which can cause the burner to go excessively lean or rich, thereby causing serious safety issues and or extreme waste of the fuel energy spent. For instance, looking at the chart on the screen now, see how a change in the ambient temperature from 40 degrees to 120 degrees causes the excess air to swing from 25.5% to 1.1%, all without our control. And this is after setting the burner at 15% with the boiler room at 80 degrees. Remember, when speaking about too much excess air, that combustion only requires oxygen, and air contains about 21% of it, but also about 78% nitrogen, which does nothing for combustion, but it only robs BTUs from the burner and sends them through the stack and out to the atmosphere. Therefore, we want to limit the excess air as much as possible while remaining safe, but we also want to do this for other reasons, which I can point out with this slide. Going in a clockwise direction, you see the air component for combustion combining with the fuel and ignition, which if the fuel is oil, will contain hydrocarbon and some amounts of sulfur and fuel-bound nitrogen. And if it's a natural gas, well, it's a hydrocarbon being burned. And then once the fuel and air are mixed together and are heated by the pilot, we have combustion, the result of which releases heat plus the effluent and emissions that are indicated in the respective oblong circles, which then exit the stack. Point is, if you're burning efficiently, what comes out of the stack is mainly CO2, carbon dioxide, and water, plus the emissions that were indicated just before and we'll talk about. But if the burner has gotten out of tune and or the uncontrollable atmospheric conditions have caused it to burn extremely rich with very little excess air, this can happen. Carbon monoxide and or soot formation, the combination of which is not only extremely inefficient and costly, but also very dangerous as well. For instance, in looking at this chart, you see the point of stoichiometric combustion marked by the red arrows. This is 100% combustion efficiency. Now, by the way, we're burning natural gas in this example. Okay, now refer to the solid black line. It represents the carbon dioxide being generated, which at maximum with natural gas is 11%. Now look at the dashed line. That's the amount of excess air, also referred to as excess oxygen. 15% excess air is the same as 3% O2. And then we have the dotted line representing carbon monoxide, CO. So what this all means is that as we drift to the right of stoichiometric and beyond 15% excess air, we get a lean, inefficient burn. And as we drift to the left of the curve, we get a rich burn forming soot, which covers the heat transfer surfaces, substantially reducing heat transfer, and also forming carbon monoxide, which can be lethal. Here, let me show you. First, understand that we in the industry strive by design to limit CO formation, or carbon monoxide, in our package boilers and burners to close to zero and never above 50 parts per million. Now, looking at the chart on the screen, you see exposure time in hours across the bottom horizontal and carbon monoxide parts per million on the vertical to the left. Note now the red arrows marking 100 parts per million of CO and 1,000 parts per million. And then follow those horizontal lines across to the right, lining up with the exposure times. You'll see at 100 parts per million CO, exposure at 7 hours causes some sickness. But at 200 parts per million, for this same amount of time, it can be deadly. And in the more extreme case of 1,000 parts per million, which does happen, it is extremely deadly, and it only takes 90 minutes of exposure. So carbon monoxide is certainly nothing to mess with in a confined boiler room. Which then takes us back to our combustion slide. And what else can come out of the stack because of the chemical reactions encountered while burning these carbon-based fuels? You see they are nitrogen oxides, NO and NO2, and sulfur oxides, which, by the way, through many iterations of the Clean Air Act since the early 1960s, the government is mandating control over, in addition to other contaminants within our environment, as you can see on the slide.